can present some results about applications. This is maybe what many of people that are here are interested in. So we go from the pure mathematics to the time series world. And yeah, basically what I'm going to do is to answer this question. Did we use the right approach to define extreme value theory, to define extreme? When we talk about data sets this time, we are not in the dynamical system frameworks anymore, but we can start to say what we want. We want to define, of course, when an event is extreme, but what we want more is to compute how likely its recurrence. We want to know when is the next storm, so we can plan better our next meeting at Cambridge and avoid travel problems. But what we haven't done maybe so carefully up to now, we have used the statistical theory, which is designed for independent and identically distributed variables in the situations for time series where this idea is not really true. In fact, we are dealing with variables that usually have correlations, and this correlation, of course, affects the convergence to the statistical theory we want to check. And also, if we consider the classical statistical theory, usually we can fit our data to a distribution, which is the distribution that Sandro showed before. I'm going to repeat this soon. But we cannot really check if we are in an asymptotic regime, so what is the meaning of the parameter we fit somehow? But what we could do, maybe, is to start to build a new extreme value theory based on the results we recently got on dynamical systems, and so take from the method itself a check of convergence that tell us if the dataset we are using is large enough to do the extreme value theory. And I'm going to explain you how in this presentation. Basically, we will go from the dynamical system setup to the time series analysis. Then I will basically recall, but very quickly, the point of the extreme value theory, because maybe I'm using different notation with respect to what is done before. And then I will try to define what we did with Sandro, an extreme value theory somehow for time series, and then maybe some conclusions, some outlook that I want to share with you. So usually we have this problem when we go from the dynamical system world to the real world, that in this low-dimensional dynamical system world we know the properties of the attractor we are studying. So for example, the maps that Sandro showed before, we know that there is a Lebesgue measure, we know that there is a fractal measure if we take EFS, the generate counter set, and so on. But in the real world, what we really have is a complex system where we have spatial and temporal chaos, and we have interaction of different time and spatial scale. So how do we match these two worlds? That's always the problem. We can define a very good set of tools to study this kind of systems, but how do we really go to the next step? It's a big problem. And so this is basically what I just said, so that usually when we have a time series, when we extract data from observation, or also from models, climate models, we can extract time series, but we don't know the properties of the phase space we are living in. So, and the measurements, when we talk about real data, are also perturbed by this instrument error. So this is something we should take into account when we want to build the theory. So what we do traditionally is to take a pure statistical approach, really do statistics, and extract from the statistics some information on the dynamics. But the statistical properties we extract should somehow match some quantitative properties of our systems. And we have a clue that low-dimensional models can be used to model some important features of spatial temporal chaos or much complicated systems. So what I'm trying to do is to basically discriminate what is a real extreme event from a natural variability in time series. This is a specific problem I will focus on with respect to this big problems that there are between matching the low-dimensional dynamical system words and the high-dimensional dynamical system words, how it's by basically defining a rigorous approach to the study of the time series, or something that is maybe more rigorous than just plug a statistical theory for IID variables in a non-IID setup. And why? Because there is this gap between the definitions of properties in low-dimensional dynamical system and in real world. And what I use basically the theoretical setup that has been described by Sandro, and I will try to convince you why maybe this reformulation of the extreme value theory in terms of observable dynamical system may be useful. And basically the reason why is because these techniques, as you may have already basically understood by the presentation of Sandro, say already which distribution we have to expect if we use some kind of specific observables. And so the other point is that I somehow get rid of the complexity introduced by the fact that I'm studying a problem in a phase space was embedding dimension, I don't really know, because the dimension enter here just as a scaling parameter. It doesn't really enter as something that affects itself the convergence. So before starting, of course, with extreme value theory for dynamical system, I recall what is extreme for me, and I will consider the so-called block maxima approach. So I will take a time series which has a key observation, and I will divide my time series into n intervals, each containing m observations, and on each of these intervals I just take basically the maximum or the minimum, and so I can really do the statistics like this. And then I check, of course, Sandro was talking already about the limiting theory, which means I send n to infinity and I send m to infinity. In these limits, I get, if my variables are independent and identically distributed, convergence to the so-called generalized extreme value distribution, which is here represented with this different set of parameters, where psi is the shape parameter, mu is the so-called location parameter, sigma is the scale parameter, and of course the most important thing is that psi really determines the kind of extreme value distribution we can get. In fact, if our global distribution, the distribution of all the data, behaves well, so the tails somehow can be identified, we have only three possibilities. One possibility is that we have exponential tails, and so we are going to get a gamma law. The second possibility is that we have power law tails, and then we are going to get a Fresnel law. And the third possibility is that we have tails bounded from above, in which case we get a Weibull law. This is, I say, is for the independent and identical distributed variables. What are the issues when we consider a discrete time dynamical system? So, in general, we can define like this, and we take the initial condition if zeros. The problem is we can identify the time series as mixing stochastic process, but we have to recover somehow the independence by imposing some mixing condition of the series. Otherwise, our distribution of maximum will never be sample like it is IID. The second point is that the theory I'm going to use is this theory with basically designed for observable of the distances among the points of the trajectories. The reason why is that I said at the beginning, I want to compute the recurrences of extreme events. So, if I have observable of the distances between a point of the attractor, I'm really looking at the recurrences, and I will try to convince you that it is like this. So this is observable we already seen before. So it was introduced, as Sandro said, by Pierre Collet, and after being expanded by the theory of Freidach and Mike Todd. And basically, The only things we require to this kind of observable is that are monotonically decreasing. And you see, it's nothing that just compute taking the maximum of this observable means taking the minimum distances from the point zeta, which is the point of the attractor. So it means really sampling some kind of recurrence properties. So whenever I go close to a point of the attractor, I sample a maxima, and then I do the statistics of this maxima, and I get basically one of the three laws. As Sandro has shown already, by choosing the logarithm, this kind of functional form, we magically get already a Gamble law. And the Gamble law say that we should get, in the setup I described before, here, a shape parameter C that goes to 0. And more important, I have also a link with the local dimension, which is basically given by the reciprocal of the standard deviation. But so you see that here I don't have any dependence on the dimension of the system. So if I have any kind of system, I just can check that there are enough recurrences around the point zeta by checking if I get a successful fit to the Gamble distribution. And this is basically the argument I'm going to use in time series. Again, I try to explain the link with the geometry and what is in some sense the bin length. In fact, the maxima of this observable defined like this are entrances in a ball centered around the point zeta of this part of the attractor, which is represented in blue. For different bin lengths, what happens? Well, it happens exactly that if I take a very small bin length, what I'm going to see is basically I'm going to see a maxima that is not really close to my point. But if I go to infinity, I have really statistically more chance to go close to the point zeta, and so to sample a point which is closer to the one I've chosen. So if I measure, for example, the local dimension, and I take a larger bin length, I may hope to get better estimates, of course. And this has been basically addressed in a work by Valerio, and I was also called. But how we can really adapt this theory to time series? Because I said I'm going to talk about temperature data, but we haven't seen so far. So let's try to adapt in a similar fashion what has been done already for the definition of the Lyapunov exponent. And basically, we have to take into account two things when we go to time series. One is that, as Sandro says, we have dynamical noise. So the dynamical noise is not the observational noise, it's the noise introduced by the fast scale that we don't really sample or that just give us a kick if we look at a particular time scale. But of course, here there are people that know better than me this. And in the case of temperature daily data, this can be seen as the meteorological effects on the seasonal cycle, which is instead the large scale effect. And the other thing is that, of course, we use a thermometer, so we have also the effect of observational noise. So at each instant, our system remains on the attractor because the atmosphere does whatever it wants, but what we sample is somehow a displacement given by the thermometer, and also we have a truncation error given by the fact that the thermometer is somehow imperfect instrument. So in the most general case, which is slightly more general than what Sandro showed, what we have for an observation at the time t, it's some kind of deterministic part which comes, now we assume that is Markovian, so from the previous observation, and then we have to add some noise to represent the fast scale, but also what we really measure is this, it's y of t, which is affected also by this psi of t, which is, for me now, the observational noise. So this is the system, whatever, I cannot really affect the system because this is the atmosphere, let's say. And then I use a thermometer and it gives me y. And that's what I have, and I'm going to study. I'm lucky because it has been proven, and also this was part of my PhD thesis, that the theory Sandro presented works for mixing system if they are perturbed with dynamical noise, but also when you have a periodic or quasi-periodic system, which is the case of the temperature, because we have the seasonal cycle, and we add noise, which here is given by the meteorology, the theory works, so we find the same extreme value laws. But also, as Sandro has shown in this presentation again, we have also that it's going to work also for observational noise. So, what is the problem with time series now? The problem is that we cannot do the limit. We cannot send m to infinity. We cannot send n to infinity. So we have to deal with the data sets we have. And how we can check that the number of observation is enough to sample a real extreme event, and we have a sufficient number of maxima. But we can just check if we get the Gumbel law, as we said before, because if we get this shape parameter equal to 0, we do a Kolmogorov-Smirnov test, and we have a successful fit, then we know that we are in the asymptotic regime. And basically we found that this holds already when we have at least 100 maxima, and each of these maxima is taken at least 300 observation, even if we say that the optimal is to have already 1000 maxima in 1000 observations. So this, basically, all this I presented in the last two slides legitimate somehow to me to use this theory for time series, because time series I can see as the output of a dynamical system perturbed with dynamical noise and measured by an instrument which is imperfect and add observational noise. So I'm trying to do this, and I basically define this algorithm. That is, I take a time series that has S observation. I fix a point zeta, because remember that we have to compute the distances between the orbit and the point zeta. And this point zeta now is a point of the series itself, okay? And then I compute this series of the distances between the point of the trajectory and zeta, and I apply the logarithm. Then I divide the time series into bins. I extract the maxima of this observable, which again corresponds to the minimum distances to the point zeta. And then I fit to the generalized extreme value model. And then there are two possibilities. And here we go. If the fit succeeds, then it means that there are enough recurrences around the point zeta. So this point somehow is a normal point of my system. It's not so special. In the time fixed by the bin length, so the window on which I extract my maxima, basically I have enough recurrences around the point. And then I can decrease the bin length to find the minimum bin length such that my point somehow can be considered normal. But if the fit fails, then what can I say? That the recurrences around zeta can be considered as extreme events, because I don't get really enough recurrences in the bin length. And so this time I can increase the bin length to see if that point that I defined as extreme enters in the normal variability of the system when I increase the bin length, okay? So let's see what's going on with the temperature data set. I just present you the data set. So these are 4 years. It's mean daily temperature and mean daily temperature anomalies. These are just computed by removing this seasonal cycle. This is the distribution, and this is taken at Armagh in the United Kingdom. And basically what I'm going to do is to take a point, each point of the series, and to compute the recurrences around the point and see if I have enough recurrences by changing the time window on which the maxima is taken, basically. Maxima, that I repeat again, correspond always to the closest observation to the point. And what I get is basically this picture. So, on the x-axis I have the bin length in years, and on the y-axis I have the temperature. These red dot lines are the absolute extremes of the time series. The blue area is the area I define as normal variability of my system with respect to the time scale fixed by the bin length. The point in the white area between the two dot lines are my extremes. Why? What does it mean? So this is UK, the first plot refers to UK, this station that I've chosen. The second point is a time series of Milan, and the third plot refers to the time series of Vienna. What we see is that, for example, if we take a bin length of half a year in UK, we can already see that there is a small interval of temperature, because between, let's say, 17 degrees and 12 degrees, if I remember well, for which I have already enough recurrency. So my fit succeed, and I can define basically this temperature like normal temperature. And maybe this doesn't really go against your experience, because if you think about it, that's what you get in this country basically most of the time. And in fact, if we instead go to Milan or to Vienna, I see I have nothing below half a year, because the variability of the seasonal cycle is so high that in fact I jump and I don't have enough recurrences around in a half a year, because half a year is cold and half a year is roughly much warmer than that. When I go to 1 year, that is usually what we do, the reference to do extreme value analysis, I see basically that I can get somehow some, I get some difference that will be clear in a moment, but the things of course change when I move around, when I move toward 4 years. So temperatures that can be defined as extremes for a bin length of 1 year are not extremes if I consider 4 years. So I expect that an event which is located here has enough recurrences in 4 years, so it's not an extreme, but it's an extreme if I look 1 year bin length. So these allow me to link the extreme to some kind of recurrence properties, and I'm getting, and I know that I can do that because I get a Campbell law. What else I can do with this? I can play with the temperature anomalies, which was basically the other time series I show, which looks like noise. In fact, is I subtract the seasonal cycle, and in fact, if I do this, I can compare the station, because somehow I'm looking only the anomalies. And if I plot, so I fix myself here, I take 1 year, and then I plot the width of this interval, okay, for 60 stations located in Europe, and then I do some interpolation. What you see is that I can see some difference, some relevant difference between the area located at marine location, like the coast of Italy, Ireland, Scotland, UK, and this part of basically Brittany. And you see that here, basically, this width is not that large, because the fact that I have an ocean really doesn't make my seasonal cycle, and so my anomalies fluctuation as well that high. But if I go towards the continent, I see higher fluctuations, and it's remarkable that we get, for example, this gradient here in the Iberic Peninsula near Madrid, and this is because we have a mountain range where we again have some section is located at 2,000 meters, some section is located into the valley, and so you can see also these very sharp differences between them. Okay, so this is something basically you can do, and basically this is the end of the story. In fact, basically by using this technique that goes from dynamical system to the real world, the real data set, we built up something that is, we start to prove by absolutely continuous invariant measure. Then we add dynamical noise, so fast scale processes. Then we add observational noise. And then we say, okay, now maybe this is enough to try with time series. So we tried with time series, and in fact, it seems that we can say something about the extreme behavior of around the point of our time series. And what is nice is that is the time series itself that tell us if we can really do the analysis or not. Look, that here I stopped 4 years, because after I get that the Kolmogorov-Smirnov fit diverges. And of course my time series are not that long that I can do extrapolation, longer extrapolation. So what are the outlooks and what are the open questions? Okay, here I use temperature, it's very nice. We know that there's a continuous support. That's important because Sandro was saying that somehow this is a requirement that we need to do this analysis. But for example, what happens if I take variables that has a stranger support like precipitation or wind? We know the distribution of the wind is completely different with respect to the distribution of temperature. So these are all things to rise. And then, for example, the other things is that, okay, what is a very first approximation of a spatial temporal chaos is a lattice. So it would be nice, for example, to define now an extreme value theory in systems that are lattice. And I don't know if I have still some time left.
Yes.
How many?
4 minutes.
Okay, so I can show you, for example, I thank you for your attention now, but before I show you what happens if we try to do the traditional extreme value theory, and we try to fix, for example, this kind of maxima, which is something that Valerio suggested, actually. If we try to fix, these are basically the global extremes of our time series, but if I do the Pareto approach, so the peak over threshold approach in a classical way, so by changing the threshold and so on, I can define basically a level which corresponds to the classical extreme value theory. And so basically Valerio asked me to do this test, and this is the script that does it, and we run it together now. And we just, you see, what I'm going to do is just, I define a threshold, I resort the time series, because in fact, the Pareto distribution doesn't keep any information about the time structure of the time series. So I just resort my time series, and then I take different threshold, and I will plot the shape parameter for different threshold, and see where it converges to a value. And I do it now for Milan, and let's see if it's working. It's thinking. Okay. So you see, okay, this is if the threshold is at the 80% of the data, the 90% of the data, the 96% of the data. So for me, the threshold, okay, here, when it's stabilized, this is a definition somehow of asymptotic regime. You see that also this distribution is, as we were saying before, is a gamble. So with a small parameter, so somehow the torque of Tobias this morning we can find in this plot again. But if I do it instead for Vienna, what happens? We have a small problem. If Mappland, yes. Where is the threshold? So here I have problems in defining the threshold with the classical method. Instead, with my method, I will get, for some interval of temperature, some zeros, or some point zeta that passes my Kolmogorov-Smirnov test, and so that I will be happy with that. But here, if you ask me now what is the threshold, so this is the temperature I will pick up from that, I say, I don't know. I finish. Thank you.
Thank you very much. And we have time for discussion, so please.
Correct me if I'm wrong, but so you were classifying whether something was an extreme event or not.
Yes.
So the definition kind of depended on the dynamics you assumed.
I didn't assume any dynamics because I didn't introduce any parameter except.
Didn't you have something that you showed at some point, the dynamics plus what you would call dynamical noise?
Yeah, that's the most general assumption I can make on the dynamics.
Well, but you had only additive noise coming from the.
Okay.
So what if you changed that? What if you made it more?
We didn't try for.
The question is, would your definition of what constitutes an extreme event change if you changed this? Would it be?
Attention, but I define this as a possible model, but I never used it, so I just fit the data to the time series. So if the noise is not of this type, what I can say is that the answer is given by the dataset. So since I get a good fit to the extreme value law I want to fit, even if the noise is not additive, it means that it should work. So maybe with Sandro, with Valerio, or with Tobias, we have to work to find the extreme value law for multiplicative noises, right? Or other kind of noise.
And just one comment on the use of the Kolmogorov-Smirnov, because the point is that if you base the thing on the smoothness of it done with the Kolmogorov-Smirnov, then the one problem might be that the Kolmogorov-Smirnov test is not really, the best one for this kind of distribution. Plus, the other point is that when you have the shape parameter that is close to zero, let's say slightly negative, slightly positive, then you really need a lot of data, so very large sample size to distinguish between these values to really say, okay, I have a negative shape parameter, I have a positive shape parameter, so you really need a lot.
It's
and when I say a lot, it's
different.
really thousands of values.
So I can sketch it here because I cannot find the MATLAB script, otherwise I can show you how I do with the result. But basically I have, let's say that this is C and this is 0. Then I have sigma, which is 1 over d, in this case is 1 because I just project everything on one dimension, 1. And then I have the Liliford parameter or the Kolmogorov-Smirnov parameter or whatever test we can do. Okay, and so this is basically, if it's the Kolmogorov-Smirnov parameter, it should go to 0. And this is the minimum temperature, so it's T min, it's in the red bar I showed before, and this is T max. What I really see is something like, I have the confidence bar on the estimation of the parameter. So what I really see is something like this. Oh, I can really identify by eyes the part, even, it's clearly visible what is convergent or slightly convergent and what is divergent. Then you have the Kolmogorov-Smirnov parameters that basically goes with this idea. But of course, this can be improved if you have to do it for a real operation, in a real operational setup, and so on. I think one should use best statistical techniques to be really sure what are the boundaries, because 1 or 2 degrees can be very different. But this was just to show that somehow the method can work.
Yeah, for temperature it's quite clear because anyway, usually you have negative values of the shape parameter. The point might be, for instance, for other variables, that it might be very important to really say to distinguish.
Yeah, sorry. Let's try.
Yeah.
Yeah, I guess I'm a bit skeptical that you can really separate what you call a real variation from a natural variability, because the spectra, lots of people have looked at the spectra of this type of data, and you get, if you ignore the annual cycle and the harmonics, you get very nice power law spectra. Also, if you look at probability distributions of the fluctuations, you don't get a bimodal distribution. You get a continuous distribution. So it seems, if you separate it, it should be more of a theoretically based separation, and so dependent on your model and things like that. But it doesn't seem you can do it just.
This is an approach that for me it really goes back to the original idea of Poincaré of watching the recurrences. Then we do just the statistics of recurrences with the data sets the results that we have. We cannot. It would be nice to try on larger data sets.
But the real phase space is huge, so you can't see a true recurrence. That's the problem.
But this is I don't think it's true because. Still, the projection should keep some relevant information about the dynamics. Why the projection?
Looking at a tiny subspace of the process.
Yeah, but somehow, why I don't use directly the theory of Poincaré? Because there, for example, when you do the heating time statistics and so on, everything is mixed up in the exponent. So you can say, I can fit the exponential decay of correlation and so on, but there you have the embedding dimension, and you have somehow to compute it because it changes the rate at which the decay happens. And where do you stop? So me personally, I'm skeptical with methods that have to deal with embedding dimension because I never find this minima of this function that allows to minimize. But we can discuss about it.
Okay. If there are no further questions, thank you again.
Thank you.